Hello everyone, welcome back to Z Physics. Today we're going to be going through the solutions of the written questions of the 2019 OCR Breadth in Physics paper. Just a little note that if you're looking for the multiple choice question solutions, I've done those in a separate video, and you can find that in a link in the description of this video. Well, let's get started with question 21. So first off, we have a system, and in order for that system to be in equilibrium, one of the conditions is that the resultant force must be zero. State another condition that must be satisfied. Well, the other condition, and there are only two for a system to be in equilibrium, is that the sum of the clockwise moments must equal the sum of the anti-clockwise moments. The next question is really interesting. We have figure 21.1 shows a ball at a rest on a horizontal table. Now the weight of the ball is W and the normal contact force on the ball is N. According to Newton's third law of motion, W is one of the forces in a pair of equal and opposite forces. Name the object that experiences a force of magnitude W but in opposite direction. This is actually a little bit of a trick question. The correct answer is actually the Earth. Now let me give you a little bit of a different example in order to visualize it. Now imagine that you have, let's say, the Earth and then another object. Doesn't have to be this ball, or let's say it could be the moon, or it could be sort of any other massive object. The object will be attracted towards the Earth, it will be falling towards the Earth, and that force is expressed by the weight. Now the Earth will also experience a force of the same magnitude pointing in the opposite direction that will be equal to the weight. So those two arrows are of the same size. However, because the Earth is so much more massive, it will hardly be affected by this force. So when the ball is actually falling towards the Earth, in a way the Earth is also moving towards the ball. However, if we were to actually calculate the acceleration of the Earth, it is absolutely unmeasurable. So part 2, according to a student, the weight being equal to a normal force is a consequence of Newton's third law of motion. State why this is incorrect. I've actually addressed this question in a longer video on one of the most common Newton's third law misconceptions, and I will also provide a link to that video in the description. Really interesting question, but in a nutshell, why is this incorrect? Two reasons. First off, both forces, both the weight and the normal force, are acting on the ball. In a Newtonian pair, there are two forces which act on two different objects. For instance, let's say we have object A that is moving and it's colliding with object B. Now, when they're colliding, object A will experience a force due to object B, and object B will experience an equal and opposite force due to object A. Here on the right, we have a Newtonian pair, and we have two different forces acting on two different objects. Over here on the left, you're going to see that we have two different forces acting on one object. So this can't be possibly a Newtonian pair. Furthermore, those two forces, W and N, are of a different type. And Newton's third law says that these two forces that are a consequence of Newton's third law have to be identical. For instance, W here is a gravitational force, and the normal reaction fundamentally actually is caused by electrostatics, and additionally by an effect called the Pauli's exclusion principle that says that no two electrons can occupy the same quantum state and therefore cannot be in the same position. So this is what is ultimately causing the normal force. So just to summarize, both forces act on one object and they're of a different type. Let's have a look at the next one. So figure 21.2 shows a model dolphin in a museum, and the dolphin is held in equilibrium by two different cables, A and B, and we're given quite a lot of forces here. So we have a 68 Newton force acting this way at 10 degrees, then an 87.4 Newton force acting at 50 degrees to the vertical. Now what the next bit is asking us to do is to calculate the total vertical force applied by cables A and B by resolving the tensions in the cable A and B. Okay, well, let's do this. Now when you are taking the exam, you should always write down your answers within the space given for this, but just so that we could visualize what we're doing, I'm just going to find the total vertical force right next to this diagram. Okay, well, there are two vertical vectors. One of them is going to be this one here, then another one, if we were to resolve this one, let's resolve it along here, will be this one over here. So the total vertical force will be found by this one plus this one here. So in order to find the first one, this is the opposite, so I'm going to do 68.0 times the sine of 10 degrees plus, and now there's a little bit of a trick, we're looking for the adjacent component. So what we need to do is do 87.4 times the cosine of 50 degrees. In general, anytime we're resolving vectors, what we need to do is multiply the hypotenuse by either the adjacent or the opposite component. In the first case, it's the opposite component, so it's hypotenuse times the sine of 10 degrees. For the second one, it is our hypotenuse, which is 87.4, times the cosine, because we're dealing with the adjacent. Putting this into a calculator, we are going to get 68 newtons. For the next part, we want to use our answers, so 68 newtons, to calculate the mass of the dolphin. Okay, that's not so bad because we've calculated the total upward force. Now, because the object, the dolphin, is not moving, the sum of all the vertical forces is going to have to equal the sum of the only force which is acting downwards, and that is, of course, the weight. So we already know that if this plus this is 68 newtons, then the weight will also be equal to 68 newtons. So in order to find the mass, all we need to do really is say that our weight is equal to mg and our mass is equal to the weight divided by g, so that's going to be 68 divided by 9.81, and this is of course equal to 6.9 kilograms. So the answer is 6.9. Part 3, this is a really interesting question. We have the cables A and B have the same length and cross-sectional area. The material of cable B has Young's modulus 1.29, where E is the Young's modulus material of cable A. Calculate the ratio of the extension of B to the extension of A. Now remember, anytime we have a ratio, we should just confidently work through it, not worrying too much, because something is going to cancel out eventually. Well, let's start off just with the two Young's moduluses. So I'm going to do Young's modulus of B divided by Young's modulus of A. Well, this is equal to the stress over strain of B, so stress of B divided by strain of B, and then that's going to be divided by the stress of A divided by the strain of A. Well, let's just work for this fraction a little bit. So remember, if we're dividing by the fraction, it's the same as multiplying by the inverse. So this will be equal to stress of B divided by the strain of B times the strain of A divided by the stress of A, like so. Okay, well, we're almost there. This will then be equal to the stress of B, which is force over area. The force is going to be different, so I'm going to give them a subscript. Let's say that this here is force B, and the strain will be given by xB divided by the length times the strain of A, which will be XA divided by the length, and the stress of A will be the force A divided by the area. Now, because the question says that they have the same length and the same cross-sectional area, excuse me, I can actually cancel these out like so, and what I'm left with is FB times XA divided by XB times FA. So I'm almost there. Now focus on this part of the fraction. I have EB over EA actually equals this expression. Well, EB over EA is actually equal to 1.29 E divided by E, and this will equal FB times XA divided by XB times FA. Okay, so we can cancel all the E's as well, and what we're left with is 1.29 is equal to FB over FA times XA over XB. Okay, and all we need to do really is, because we're looking for the extension of cable B, is just to bring the XB's on the other side of this equation. Let's simplify this even further. We know that 1.29 is equal to FB over FA. Well, we know what FB is. That is just 87.4, and FA is, so FB is 87.4. So 87.4, and FA is 68. Well, hang on a minute, we can just divide this ratio and sub that in. So FB over FA is 87.4 divided by 68, and magically this is actually equal to 1.29 up to 3 significant figures. So this is really important because we can directly plug that in here, because now we know that FB over FA is actually equal to 1.29 as well, times XA over XB. Well, if we just rearrange that, we get that, well, let's just cancel all the 1.29s. We get that 1 is equal to, well, 1, because those guys cancel out, times XA over XB. In other words, if we just flip everything around, XB over XA will have to be equal to 1, which is our final answer. Question 22, we have a metal ball is released from rest and it falls vertically towards the ground. The figure shows the variation with time t of the displacement of the ball. We don't have to worry about air resistance. The ball hits the ground at 0.5 seconds. Describe and explain the variation of the velocity from t is equal to 0.2 up here to 0.7 seconds. Well, this is a graph of the displacement against the time. The first factor that we need to consider is that the velocity is the gradient of the tangent of this graph. Notice here, so from 0.2 to 0.7 seconds, the velocity is negative, but the magnitude is increasing. How do we know that? Well, the gradient of the tangent along here is negative. The graph is sloping downwards. Notice though that the magnitude of the velocity is increasing because in this section of the graph, the ball is just falling vertically. So this is what happens up until 0.5 seconds. The ball is increasing its velocity, however the velocity is negative. From 0.5 to 0.7 seconds, the velocity is positive, which means that the ball has rebounded and is now moving in the opposite direction. Additionally, from 0.5 to 0.7 seconds, the velocity is smaller because the gradient is just not as steep. So if you compare this gradient here with this gradient, you're going to notice that the one after 0.5 seconds is not as steep, and therefore the velocity of the ball will be smaller. Okay, part B, use an equation of motion to show that the speed of the ball is 4.9 meters per second just before it hits the ground. Well, the equation that we're going to use is that v squared, the final velocity, is equal to u squared, the initial velocity, plus 2as, where s is the displacement. Because the ball was dropped from rest, u is actually 0, which turns this equation to v squared is equal to 2as. Now v will be equal to the square root of 2as. Now we know what the acceleration is, that's just the gravitational acceleration. What is the initial displacement? Let's have a look from the graph. Okay, well, the initial displacement is just above 1.2, so this will be equal to the square root of 2 times 9.81, and the initial displacement was about 1.23. Now let's put this into a scientific calculator, and we're going to get up to two significant figures, 4.9 meters per second. Okay, so the next part is asking us to draw a suitable tangent to the curve in figure 22 and show that the rebound speed of the ball is about 3.5 meters per second. Well, I've done this over here, drawn the tangent, and what we need to do for this is to align our ruler with the very moment when the ball rebounds. Now the gradient of this line that I have over here will tell me the speed of the ball at the moment at which it's rebounding. As always, when we're taking our gradient, we are going to aim to take some large gradient triangles. So let's do this. Let's have a look at some data. I'm going to notice that I've taken the largest possible gradient triangle, so this goes over on this side with the displacement going from 0 to 0.88. So this means that my change in displacement, my gradient, change in displacement over change in time will be equal to 0.88. And now the time changes from 0.75, take away the initial, which is 0.5, and this means that this is equal to 0.88 divided by 0.25, which is equal to 3.52 meters per second. So let's have a look at part D, the final part of this question. Calculate the average resultant force acting on the ball during the collision. Well, this is a classic impulse problem. Remember, our impulse is equal to the change of momentum. Our impulse is given by the average force multiplied by the time that it acts on, i.e. the collision time. So F times delta T will be equal to our change of momentum. We could rearrange this equation for the average force F, and we're going to get that F will be our change of momentum divided by the time that the force is actually acting for. Our change of momentum will be equal to the mass times the final velocity, take away the initial velocity, divided by the time that the force acts on. As I'm writing this, I'm going to be really careful with the signs of the speeds. Now, what do I mean by that? Initially, when the ball is going towards the ground, the velocity is negative. Now, when the ball rebounds and goes back up, our v is going in the opposite direction. So this means that our initial speed is negative and our final or initial velocity is negative and our final velocity is positive. Now let's plug in some numbers. So our mass is given up here in the question to be 56 grams and our time of impact is 1.8 milliseconds. So this means that our mass will be 56 grams, so that's times 10 to the power of minus 3, and our v, we've already found the final velocity to be positive 3.5 meters per second, and our initial velocity was 4.9. However, 4.9 in the opposite direction. So this will be minus negative 4.9 divided by delta t, the time of impact, which is 1.8 milliseconds. So that's going to be 1.8 times 10 to the power of minus 3. This, of course, will be equal to 56 times 10 to the power of minus 3, and the two minus signs are actually going to turn into a positive. When we plug this into a calculator, what we're going to get is about 261 newtons. In this question, we're working up to two significant figures, so we're going to leave that as 260 newtons. Question 23, we have a cell of an EMF 1.4 volts and an internal resistance of 0.62 is connected to two resistors A and AYB. Now the resistance of resistor A is 1.8, like so, and the resistance per unit length of YB is 9.5. The length of the wire is 40 centimeters, which is 0.4 meters. So this means that the value for the resistance of B will be equal to 0.40 times 9.5, which is of course going to equal, when we put that into a calculator, to be 3.8 ohms. Okay, now if this guy is 1.8 and B is 3.8, what we need to do is find the resistance within the circuit. So the resistance within the circuit, because A and B are connected in parallel, R will be equal to 1 over 1.8 plus 1 over 3.8 raised to the power of minus 1. This is just a formula for adding resistors in series. So let's put this into a calculator. 1 over 1.1 plus 1 over 3.8. Don't forget to raise everything to a power of minus 1. And the resistance within the circuit will be approximately equal to 1.22 ohms. Now, once we have the resistance of the circuit, we are ready to calculate our current. The formula which we're going to use is that the EMF is equal to our current times the resistance in the circuit plus the internal resistance. Well, let's rearrange for the current, and what we're going to get is that the current is the EMF divided by R plus R, and our EMF is 1.4 and our R is 1.22 plus 0.62, which is the internal resistance of the circuit. When we put this into a scientific calculator, we are going to get 0.76 amps. Part 2 of this question, calculate the ratio of the power dissipated in the internal resistance divided by the total power of the cell. Okay, well, this ratio will be given by, well, we can find the power dissipated in the internal resistance by the equation that power is equal to I squared times the resistance R. Now, rather than just R in general, I'm going to write the internal resistance R. So our power dissipated by the internal resistance will actually be equal to our current, which is 0.76 squared, times our internal resistance, which if we look over here is 0.62. So times 0.62. Then we're going to divide that by the total power supplied in the cell. Now for that, I'm just going to use, let's say, P is equal to VI, and our voltage or the EMF is 1.4 multiplied by the current, which is constant, so that'll be 0.76. Once we plug this ratio into a scientific calculator, we are going to get about 0.3365. So up to two significant figures, this will be 0.34. So part B, we have a question which is about two identical filament lamps. We have the IV characteristics of these lamps over here. The lamps are connected to a 6-volt supply of no internal resistance in series, as shown in this first figure, 23.3, and then we connect them in parallel, as shown across here. So the current from the supply in the series circuit is IS, and then the other one is IP. IP is found to be 3 times greater than IS, and our job is to explain why. Well, let's start off by finding the resistance. We can find the resistance using the IV characteristics by picking 2 points. So what I've done over here is I've taken this point where I is 0.5 and where V is 6.0. Using the fact that the resistance is equal to the potential difference across the component divided by the current going through it, if my PD is 6 and if my current is 0.5, then this means that the resistance of each lamp is 12 ohms. Now, the lamps are connected to a 6-volt power supply, and in the first case, they're connected in series. So this would mean that, of course, each of those lamps is going to have a potential difference of 3 volts across it, because the sum of the EMFs has to equal the sum of the PDs. This is, of course, Kirchhoff's first law. Now, each bulb has a 3-volt PD across it, so if we go over to the graph, we're going to see that at 3 volts, the current is actually 0.36 amps. And this is quite significant. So now in the first instance, we know that IS is actually equal to 0.36. When we look at the parallel case though, let's do a little bit of a calculation. Because the bulbs will now be at 6 volts at 12 ohm resistance, well, we can pretty easily figure out the current in that case, because the total resistance will be given by 1 over 12 plus 1 over 12 raised to the power of -1. This is just our resistors in parallel formula. We're going to get that the total resistance is 6 ohms. Well, our current will then be given by V, which is 6, divided by resistance 6, which is 1 amp. Well, hang on a minute, we've actually done our job here, because 3 times IS will be equal to 3 times 0.36, which is 1.08 amps, which is approximately equal to I parallel, which is 1.0 amps. So question 24, you're provided with a rectangular block of plastic, and we have some typical lab equipment, and we want to accurately determine the refractive index of the plastic block. Now I've drawn a little diagram of what we are going to do. First off, we're going to direct the laser beam and we're going to measure our angle of incidence with respect to the normal. Then we are going to measure our angle of refraction with respect to the normal. We're going to measure those angles using a protractor. Because they're asking us how are we going to do this accurately, we are going to take multiple measurements and then average. Once we have the averages of I, the angle of incidence, and R, the angle of refraction, we could use Snell's law. Snell's law says that N1 sine of I is equal to N times sine of R. Well, just rearranging for N, we're going to find that N is equal to N1 sine of I over sine of R. Now our N1 in this case is just the refractive index of air, because our laser beam is going from air to the refractive index of the block, which is our N here. Well, this means that N will be equal to 1.0 times sine of I over sine of R. In other words, the refractive index is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. Part B, the speed of sound can be determined with the following arrangement: with a stationary wave, and when we vary the frequency, and we also measure the length. Now we have a graph here and we need to draw the line of best fit and find the gradient. So I've drawn a line of best fit, and before we find out the gradient, just a quick check and notice that we have kilohertz on the y-axis. So we need to be very careful when we're calculating the gradient. Our gradient will be change in y divided by change in x. So it's going to be 3 minus 0 times 10 to the power of 3, because our frequency is given in kilohertz. We're going to be dividing that by our change in x. Notice that I've taken a very large gradient triangle, and any time that we have to calculate the gradient, we need to be very careful to do that. So that'll be 3 times 10 to the power of 3 divided by 17.5, take away 0.5, and if we plug that into a calculator, we are going to get approximately 176. Of this question, explain why the gradient of the line is v over 2, where v is the speed of sound. Well, the separation between adjacent nodes, L, is actually equal to half the wavelength. Let's visualize this with just a normal stationary wave. Notice that in this case, though, our wave is longitudinal, and I've just drawn a transverse wave here. It's the same principle behind it, however, it's easier to visualize. Now, in a normal stationary wave, let's draw the other part of the stationary wave as well. The distance between a node and a node is always half the wavelength. And you can clearly see that this distance here is half of the overall distance. Now, armed with the knowledge that the length that we've measured, L, is equal to lambda over 2, half the wavelength, the distance between adjacent nodes, we can use y equals mx plus c analysis combined with the wave equation. Now, the wave equation says that the speed of a wave is given by the frequency times the wavelength. In other words, the wavelength is equal to the speed divided by the frequency. Well, let's see whether we can convert that to a y equals mx plus c analysis. Now, L is equal to lambda over 2. This means that if we were to rearrange for lambda, so we'll just rewrite this over here. Lambda is equal to v over f. Well, lambda is also equal to 2L, and this is just looking at this equation. So what I'm going to write here is 2L is equal to v over f. Because in this graph I have a graph of the frequency over the length, I'm going to rearrange for the frequency. So this means that the frequency will be equal to v over 2L. Now, notice something. If I was to plot a graph of the frequency against 1 over L, In fact, let me just rewrite this as V over 2 times 1 over L. Let's compare this with Y is equal to mx plus c. If our frequency is on the y-axis, if 1 over L is on the x-axis, our intercept should be around 0 and our gradient should be v over 2. So our gradient m should be equal to half the speed of sound. Part 3, use our answer in part I and the information given to determine v. Well, we found our gradient to be 176, and in the previous part we said that this is equal to v over 2, where v is the speed of sound. Therefore v will be 176 times 2, that is equal to 352 meters per second. This is not too far off from the real speed of sound value, which is around about 340 meters per second, so we know that our answer is somewhere within the correct range. Now, part 4. The smaller values of L are much more difficult to determine with the microphone in this experiment, and this produces a large percentage uncertainty in the values of 1 over L. Suggest how this percentage uncertainty may be reduced by the experiment. Now, every time we have equal values, it is definitely beneficial to measure multiple of them. For instance, if this here is L, the distance between adjacent nodes, maybe we could measure the distance between 3 or 4 adjacent nodes. This would actually decrease the value of our percentage uncertainty considerably. So what I've written over here is to measure multiple distances, L, and later on divide after the measurement. So, for instance, because our percentage uncertainty is equal to plus or minus the absolute uncertainty divided by the measurement times 100, if our measured distance increases, so if our measurement goes up, this means that our percentage uncertainty will go down. Question 25. State one piece of evidence for the wave-like behavior of electrons. Now, this is the diffraction of electrons when they're fired off through a crystal or a graphite sheet. In an electron gun, each electron is accelerated to a maximum kinetic energy of 210 electron volts. Show that the final speed of each electron is about 9 times 10 to the power of 6. Well, we're going to use the fact that EV is equal to half mv squared. Now, if the electrons have been accelerated to 210 EV, this means that they would have gone through a 210 voltage of a potential of 210 volts. Just rearranging for V, the velocity, we'll find that this is equal to the square root of 2e times the voltage divided by the mass of the electrons. This is in terms equal to 2 times the electron charge, 1.6 times 10 to the power of minus 19, this should say minus 19 here, times 210, divided by the mass, which is 9.11 times 10 to the power of minus 31. Once we put that into a scientific calculator, we're going to find about 8.6 times 10 to the power of 6, or about 9 times 10 to the power of 6 meters per second. We can calculate, now that we have the velocity, the de Broglie wavelength really easily. Remember, the de Broglie wavelength lambda is equal to Planck's constant h divided by the momentum p. H is just 6.63 times 10 to the power of minus 34, given in your formula booklet, and m is the mass, which is 9.1 times 10 to the power of minus 31, times the speed, which is 8.6 times 10 to the 6. Remember, p in this equation stands for momentum, mass times velocity. Once we've calculated this, we're going to get a very small wavelength, about 8.5 times 10 to the power of minus 11 meters. For a final question, we need to look at the photoelectric effect. So, electromagnetic waves interact with matter as photons, little particles of light. Explain the photoelectric effect using ideas of photons, conservation of energy, and work function. Even before starting to write up this question, we know that we're going to have to be explaining Einstein's equation. We also know that we'll need to define the work function, and we'll also need to see how photons fit in this picture. Well, let's write up this question and have a look at the solution. Let's have a look at my solution. First off, remember, always in the photoelectric effect, we have one photon interacting with one electron. This is the one-to-one interaction between photons and electrons. During that interaction, if a photon has an energy higher than the work function, an electron is emitted. Now, what is the work function? It is the minimum energy required to release an electron from the surface of the metal. This has been placed in or written in bold, so I make sure to define it. During that interaction, energy is conserved. The photon energy is equal to the work function plus the maximum kinetic energy of the emitted electron. Okay folks, this was our final question of this paper. Hopefully you have found this video useful. Thank you very much for watching, and I'll see you in the next video.